quantum toroidal algebra actions on the Grothendieck groups of the moduli space of stable sheaves. And that the topic is a bit long, but first let us make an overview of my talk today. So we will consider a projective smooth surface. Over algebraic closed field of characteristic 0. And in this case, the Schiffmann-Vasserot, for the case the surface is P2, and the engineering goods for all the algebraic surfaces, they constructed a quantum toroidal algebra action on the Grothendieck groups of the moduli space of stable sheaves on S. And my topic today is about a weak categorification of this algebra action. So first, let's introduce what's the quantum toroidal algebra and why should we care about this action. So quantum toroidal algebra has many different presentations. So we will also call this the Ding-O'Hara-Mickey algebra. It is also the whole algebra of coherent sheaves on an elliptic curve. And it is also related to the double affine Hecke algebra. But I will introduce this in the most elegant way, and I will regard this as an affinization of the Q-Heisenberg algebra. So let's remind what's the Heisenberg algebra. Heisenberg algebra is generated by a centralizer H and some operators pi. I is not equal to 0, and their commutator is that the commutator of pi and pj is H if and only if I plus j equal to 0. This is this is the definition of Heisenberg algebra. And on this Heisenberg algebra, we can do a deformation, and we will get the Q-Heisenberg algebra. And the quantum toroidal algebra is one more time affinization of the Q-Heisenberg algebra. And so let me remind you what this algebra is. So we consider consider two parameters Q1, Q2, and we consider the fractional field over Q1, Q2. Then we define quantum toroidal algebra by the positive part EK, negative part FK, and there are also the zeros part, which we call HL. And this algebra satisfies the above relations. There are a lot of relations, and I would not ask you to remember all those relations, but I wanna remind you that it has positive part EK, it has the negative part FL, and it also has the zeros part. And moreover, I might wanna explain why this is when we regard this as a Q affinization of the Heisenberg algebra. What's the relation between this one and the Heisenberg algebra? The relation is here. For example, fix the K. We can consider EK and FK, and there are also other there are all others elements in the quantum toroidal algebra which we call the EKR. Like here, EK is EK1, but we can also consider other elements EKR. Sorry, no EKR, EKM in the quantum toroidal algebra, such that EKM and FKM forms a Q-Heisenberg algebra structure. And because we could choose K to be any integers, so in this situation we can regard this as the affinization of the Q-Heisenberg algebra. So this is what we call the quantum toroidal algebra. And the second question that because we already introduced this algebra, the second question that what's the interesting representations we should consider about the quantum toroidal algebra. This answer is closely related to the geometrical representation theory. So first, let us remind the case of Heisenberg algebra case. I mean, in 1990s, Nakajima and Grothendieck, they constructed the action of the Heisenberg algebra on the cohomology of the Hilbert schemes of points on an algebraic surface, and moreover, they prove that this cohomology could be regarded as irreducible, or more precisely, the full representations of the Hickey algebra when the surface is the affine plane A2 itself. And in this case, we should consider the Borel-Moore homology. And okay, and now we want to consider one more step from the cohomology to the Grothendieck groups. And then, this is also a general philosophy of the geometrical representation. Then we should consider the Q deformation. We should consider quantization of the Heisenberg algebra, and we see the Q Heisenberg algebra, and in fact, we consider one more step by consider the affinization of Q Heisenberg algebra, and now the quantum toroidal algebra appears here. And in this case, Schiffmann-Vasserot and Neguţ, they constructed a quantum toroidal algebra action on the Grothendieck group of moduli spaces of stable sheaves with rank R. R can be arbitrary rank. So you see that this related the representation side, the quantum toroidal algebra structure side, to the geometry side. We consider the moduli space of stable sheaves on the surface, and moreover, we can show that the operators, the positive part I and the negative part Fg, those operators are actually represented by the Fourier-Mackay kernels, which are also related to the lie bundles on some nested moduli spaces, which we will introduce further. And in this case, we already introduced EL and FJ part. So what's the H part? Actually, we can show that H1 and H minus 1 are just induced by the universal sheaf on the moduli space, and also is derived too. We will see this further, and actually we can see all other HK could be regarded as the some combinations of the batch product and the symmetric product of the universal sheaves. So this is what the quantum toroidal algebra and and its representations. Any questions? Okay, so let's so we already talked about its representations. Now, yes. Now, now we wanna talk about our topic today. We wanna make a weak categorification of this action. So what does that weak categorification mean? Because we remember that for an algebraic variety, we can always consider the derived categorical coherent sheaves on this algebraic variety, and for each element, we can associate it to a K-theoretic, to the Grothendieck group, to the K0 part of this variety. So you see that so you said that the derived category of this model, derived category of these varieties could be naturally regarded as the categorification of the Grothendieck group of this variety, because it lifted some numerical stuff to the complexities. So we see that we see that the derived category gives a categorification of the Grothendieck groups, and now we translated the geometrical the algebra language, the algebra action on the the algebra representation to some algebra actions on the on the Grothendieck group of some moduli spaces. Okay, and moreover, we know that all those algebras are all those operators are given as the given as the correspondences. So okay, so we can always lift the operators to form kernels, and this give a categorification of those operators. And remember that what is an algebra? Algebra is some elements or some operators with some relations. And then the next step is that we wanna lift those relations to the exact triangles in the derived categories. This is what we mean the weak categorification. So this is also our topic today. We wanna lift the relations, those relations to the exact triangles on the derived category of moduli spaces. So this is what we wanna do. Any question right now? Okay, then let us look at what's the relations here. So here we have a relation of the positive part, like the commutator of the E and EZ and EW, and this relation is also weakly categorified by Neguţ in his in his paper for when he constructed the action at the level of Grothendieck groups, and the commutator between the positive part and the universal sheaves part, is trivial, and I can explain why this is trivial later. And yes, and then the thing left is the commutator between the positive part and the negative part. So this is the final relation. We wanna compute the commutators between K and FL for any integers K and L. So if we can lift this to the level of derived categories, we work for we finish a weak categorification of this algebra, this algebra action. So yeah, so that's what I wanna show today. Any more questions? Okay, so here I mentioned that the positive part is also by Neguţ, and also there's another way of doing the categorification of the positive part is what we call the categorified whole algebra, and this is done by Moore Porter and Francisco Sala. Yeah, and I explain what we want to do for this part. So let us describe our results now. So as I have mentioned, we already have a surface, and we need to choose an ample divisor, and we also need to choose actually a H11 class, and I mean, when we already choose those classes, we can consider the moduli space of Giesecke stable sheaves, such that the rank. Also, we fix this rank. That the rank is R, and we fix the first term character to be this one class. Okay, now we already fixed this one, and I wanna say that the M is a disjoint interunion of some MK. So what MK is just we can also fix the second chain character, the second chain character to be K. So sorry, not the chain character, chain class, the second chain class. So MK is just the moduli space such that the rank is R, the first chain class is E, and the second chain class is K. And given those classes, I mean, we could consider almost we can consider the nested moduli space. So what's the nested moduli space? It is just we wanna make a minimum modification of this shift. We wanna fix this by some we want to make this shifts to be the same. In an open set, but we want to change the structure of the shift on one point. So this is the way that we consider the nested moduli space. We want to modify the stable shift. So here, for example, if we have a stable shift F0, how do we modify this one? One of the most naive ways that we consider close point X, and we consider a subshift F-1 inside F0, such that their quotient is just a sky character shift at the point K. And now after we made this modification, then one question appears that whether F-1 is still stable. The answer is in general is not true, but we will make some additional assumptions, which we will mention later, to make this true. So more, what we want to do is that if F0 is the non-split extension of F-1, and the sky character shift at the point like Kx, then F-1 is stable if and only if F0 is stable. This is the condition we need to construct the nested moduli space. So the nested moduli space just that we consider all those modifications. So it's here like F-1 inside F0, and their quotient is a point. Given this nested moduli space, we can consider the different from the moduli spaces of slave shift. There is a tautological lie bundle on this nested one. Such that for each close point. So you said for each close point, we have F-1 and F0, and the quotient we know is sky character shift. Then this sky we can do all those sky character shift to a lie bundle on this nested moduli spaces. So this is the tautological lie bundle L I define here. And we know that as we know that M is the moduli space, then the moduli space of stable shift, then there should be a universal shift on MK times S, such that for each point X, for each point X, when we restrict the universal to x times s, it should be the stable sheaf for the point x present. And we should also consider the canonical line bundle of the surface, because this parameter naturally appears in the algebra actions. So this is the setting we should consider. So any question right now?
I have a small question. So in the third point, you define the tautological line bundle.
Yes.
And for each closed point, F0 in F1, is it F-1 in F0?
Yes, F-1, sorry, F-1 inside
F0.
Okay,
so. Okay.
Yes,
okay.
Yes,
and
sorry.
Just remind me a little bit, what is MK in the fourth point?
MK. So MK. So you said for the moduli space we should fix the rank. We should fix the first Chern class and the second Chern class, right?
Yes.
K is the second Chern class.
Oh, okay. So in the first point, UK is a universal sheaf. You are considering the moduli space of MK instead of the nested moduli space, right?
Yes. UK is the universal sheaf on MK, not on the net. But yes, on the nested moduli space DKK plus 1 times S, there would be two universal sheaves, the UK and UK plus 1.
Yeah. Yes, okay.
But UK and UK plus 1 are the pullback of the UK from MK times S, and also UK plus 1 from MK plus 1 times S. Yes, this is an important observation. Yes.
Okay. Yeah, thanks.
Yes. So here are our settings, and now what is our result? Given this line bundles, we can also twist this line bundles by I times, and we know that we can regard the nested space DKK plus 1 as a closed subschemes of MK times MK plus 1 times S. So we just consider this Fourier chi kernels of EI, and regarding this as Fourier chi kernels, we actually regard this as a morphism from direct category of MK to direct category of MK plus 1 times S, and we could also do the reverse way regarding this as the morphism from direct category of MK plus 1 to direct category of MK times S, and this gives us the negative part FR, and here FR we will twist FR, so we will make a small multiplication. FR is Li minus R, but not L plus R. Here R is the rank this moduli space, and now the question that we want to consider the the commutator between EIFJ and the natural transformations of the EIFJ and the FJER. So first, I want to show that we do have natural transformations, natural transformation from EIF minus I plus 1 to F minus I plus 1 EI. So the case that I plus J is minus 1. And when I plus J is positive, then it is another direction. So here we have natural transformation of F minus I minus 1 EI to EI F minus 1 minus F minus 1 minus 1. So you said if I plus J is positive and I plus J is negative, the natural transformations are in the different directions. And then the second question is that what I plus J equal to 0? then it is not only a natural transformation. This transformation will split. So here we have EIF minus I equal to Fi in F minus I. Sorry, here F minus EI, and here we have some direct sum. The component here is just some sheaves supported on the diagonal. So here, let me explain what's the delta and the morphism iota is. The iota is that because this combination could be regarded as some elements in the direct category of mk times s times s. Then in this case, we can consider involution. Over s times s. So for example, if we make this, if we call this two as s1 and s2, then the involution map just mapping the s1 times s2 to s2 times s1. So here is an involution map. And on the other hand, we can also consider the diagonal embedding of m times s to the m times s times s. And why this? Why this is true? Because why we need this? Because remember that the definition of the definition of H1 is the universal sheaf, and H minus 1 is the dual of the derived dual universal sheaf. So regarding H1 as some from kernels, it's just the diagonal embedding of this universal sheaf. So this is our delta lower star. UK appears here, and we should also make some modifications because canonical bundle Q and the determinant of the universal sheaves will also appears here in this computation. So finally, so this is what we finally want to achieve. We wanna consider the commutator of positive and negative part, and we wanna make the cone as some universal sheaves on the diagonal. And we already have explained the case that I plus j equal to minus 1 equal to 0 and equal to 1. So what will happen if I plus j is greater than 1 or smaller than minus 1? In general, we will always have a morphisms from EIFJ to FJEI when I plus j is smaller than 0. And the other direction, FJEI to EIFJ when I plus j equal greater than 0. And moreover, we can make a filtration of the cones by the combination of the symmetric and the batch product of the universal sheaves UK and its derived dual. So this computation will be more complicated than above two. For the case I plus j equal to minus 1, 0, and 1 case, but the philosophies are the same. We wanna make the cone. We wanna compute cone and resolve cone by some which and related to the universal sheaves on the moduli space of sheaves. So this is the theorem I want to explain. Any more questions? Okay, then let me briefly remind you that why should we consider this? Action and this categorification. So the reason that we should consider this action is that it related to the stuff of the algebra side, the quantum toroidal algebra side, and the other side is the geometric side, the geometry of moduli space of stable sheaves on the moduli space. So because of this, we can this built a bridge between the algebra side and the geometry side. So if we have some questions about the representation theory of Heisenberg algebra, the double FI Hecke algebra, and also about quantum toroidal algebra, we can translate this into the languages in the geometry side and try to prove this geometrically. And on the other side, when we consider the geometry of derived categories, the geometry like the Zhao group, the Grothendieck group, and the derived category of this moduli space, and we can also translate this language like into the integrable or irreducibility or some other properties of the representations of the like Heisenberg algebras or also the quantum toroidal algebra. So the purpose of this is to building a bridge between the algebra and the geometry side, and we can translate the languages between each side. And this is the reason that we consider action. Then, like by consider the categorification, what we can achieve, because from the geometry side, it is very intuitive to consider like the Fourier correspondence and trying to consider their natural transformations. But why does this matter to the algebra side? The answer is that the Q-Heisenberg algebra or the quantum toroidal algebra is what we call a Hopf algebra. And given a Hopf algebra, we can associate to a solution of the Yang-Baxter equation, which we call an R matrix. And the R matrix could be related to the R matrix could be related to the not invariant. So broadly speaking, given an R matrix or given an solutions of the Yang-Baxter equation, we can associate a not invariant or a link invariant for any links up to the isomorphisms. And a very common topic we care about, linking invariants that sometimes linking invariants are not strong enough. For example, this is an open question that whether the Jones polynomial could detect the unknown. So for example, if we know the Jones polynomial of a node is trivial, whether this node is trivial itself, this is still an open question. But okay, the Jones polynomial are not strong enough. But if we can lift the Jones polynomial to some homology, such that the Jones polynomial is the Betti number, is the Euler characteristic of the homology. We will give more invariance, and we can ask that whether the homology could give us the could detect unknown. So we want to generalize the not invariant to the not homology. And I mean, there are a lot of ways of doing this, like from the four-dimensional topology, from the low-dimensional topology, from the symplectic geometry, and also from the gauge theory. But from the algebra side, this is quite intuitive way. If we could categorify a representation, I mean, or an algebra, we could lift this to the derived categories. I mean, maybe not derived, but lift this to the categories. Then then it would naturally lift not invariant or not homology to the sorry, not invariant to a not homology. And what this natural transformation means, the natural transformation would correspond to the scaling relations. So that is the reason that why we care about this natural transformations. I mean, we construct here. So the answer is that the observations in the geometry side would contribute to the not homology, to discover new not homologies and study the scaling relations between the non homologies. So that is the reason that why we care about this weak categorification. So, any more question? Okay, then for the left time, I would like to briefly explain how to prove this one. Oh, so here I should remember what's the assumption we assume here. So the first assumption is that I mean, if we consider a non-splitting extension, then F is stable if and only if F prime is stable. The second assumption is that the moduli space should be smooth. Yes, and this is a quite technical requirement, but I mean, we have to assume this due to some technical reasons, and I don't know how to remove these two assumptions right now. So, any more questions? Okay, so let me briefly explain the proof. So remember, like if we consider EK and FJ, I mean, we should consider a fiber product of the nested schemes, and for the other side of like EK and FJ, we consider one nested space, one fiber product of the nested spaces, and for the positive. For the FK and EL, we should consider another moduli space, another fiber product of moduli space. So what's this? This is what we call the Z minus one and Z plus one. So Z minus one considers like F, consider sheaf F0 is ported into consider a sheaf F1 which contains two sheaf F0 and F0 prime. And the Z plus would contains F0 F0 prime, which both contains one more sheaf F minus one, and we see that the combination from chi kernels could be represented by some elements of direct category of Z plus and Z minus, but here I should warn you that there should be some derived enhancement, which we'll explain later. And okay, and we already have Z minus and Z plus. Then a natural consideration is that okay, we have F0 prime, F minus one, F1. Why should we not like combine this? Z plus and Z minus and consider more new moduli space Y. which considers that F0, F0 prime, which both contains a sheaf F minus 1, and which is both contained in another sheaf F1. And here we of course we should assume all those sheaves are stable. And yes, and then I mean because we show that they plus present the case of EKFL, and they minus present the part of FLEK. Then we wanna like making a bridge because there's both morphism from Y to Z plus, and there's also a morphism from Y to Z minus. Then the question is that whether we could like we could make the EKFL as some drive push forward of stuff on Y. So now we like transfers, we change the problem to the geometry of the modular space of Y, Z minus and Z plus. The lucky thing is that we know that Z minus is the modular space of Y is smooth. The modular space Z minus is Cohen-Macaulay, and it has exact dimension. And moreover, we can show that it has a terminal. I mean, it is not canonical. It has a terminal singularity, and the discrepancy of the Z minus should just be R plus 1. So because this we know that Z minus is rational singularity, and we know that we can push forward the structure shift of Y to structure shift of Z minus. But Z plus, this part would be a bit more complicated because Z plus contains two components. One component is that F0 equals to F0 prime, and another part is that the closure over the part that F0 not equal to F0 prime. A fourth case of rank R equal to 1, we could show that Z plus is equidimensional, and also Cohen-Macaulay and the component that F0 is not equal to F0 prime. We could also show this part is a rational singularity, and the projection morphism from Y to this part is birational. So we could associate the structure Y to one component of Z plus, and we could associate this Dirac category structure, and moreover we can consider the natural transformations. But now the case that R greater than equal to 1 things would be more complicated. In this case, the scheme Z plus is no longer equidimensional, and because this in all the issue that first, the machineries in the birational geometry would no longer work. Not birational. The machineries in the minimum model program would no longer work. And one more, the even worse issue that to consider the combination of EK and FL, we have to consider the enhancement of Z plus in the derived algebra geometry instead of the classical algebra geometry. And in this case, as I have said that for derived schemes, we don't have a Cordero vanishing theorem, Kawamata vanishing theorem. And more, a lot of theorem in the minimum model program would no longer work here. So now we need to have a more precise structure about the relation between y and the structure of z plus and the relations of z minus. So what we finally realize, the answer is that we want to consider as some derived blocks. So what we want to show is that the y, I mean remember that the z plus and z minus always have like a diagonal part which corresponds as f0 equal to f0 prime. We want to show that y is just the blow up of z plus and z minus, I mean, through these diagonals. And here I explain what this more precise what is the more precise result. So the result is that the first we could consider smooth ambient varieties x1, x2, which contains the diagonal zk plus 1 and also zk minus 1k. So here, and we can consider the global sections Si on the I mean we can consider we can associate locally free sheaves Vi on Xi in the global sections Si, such that Z plus and Z minus are the derived loci of S1 and S2. So this gives us an embedding of Z plus and Z minus into X1 and X2, I mean, into an ambient varieties. And moreover, we want Si, I mean, is 0 when restricted to Zk k plus 1 or Zk minus 1k. Then if Si restrict to Zk k plus 1, I mean, is 0, then we can blow up this Zk k plus 1 inside Xi, and this we can also pull back this Si, and we can show that I mean because the image of the pullback of Si is inside the exception divisor, so Si would actually induce another section which I call Si prime. So this Si prime is global section we are but twisted by the minus di, the exception divisors of the blow-ups. And okay, so because we know that Z minus, Z plus and Z minus are the derived loci of S1 and S2. What we want to do is that we want to associate Y to the derived loci of Si prime, and this is also true. We can show that Y is the derived loci of Si prime. Because of this, because of this, we can relate the Y to the Z plus and Z minus in a more delicate way, but not only know like whether it's a bidirectional morphism or and thus we have more complicated relation, more delicate relation between Y and Z minus, and then for the negative part, because of this theorem, we can push forward the structure of Y to the structure of Z minus, and we can show Z minus rational singularity. So we recover the old result, and for the Z plus side, we can also relate the structure shift of Y to some complexities on the structure shift on the virtual structure shift of Z plus, and we could give this comparison. And after building this geometry, we could do the commutations. In the direct category, and finally we can induce the theorem about the natural transformations in in the Dirac category moduli space of sheaves. So here is the proof, and here I mean, how much? Okay, 10 minutes live. And finally, I want to make some more remarks here. So first, I mean, we assume some we assume that technical assumptions over here. I mean, the first assumption is necessary because without this assumption, we couldn't even define the nested modular spaces. But whether the smoothness of the modular space is essential, I don't know, and I want to remove this assumption S in the future. But our proof essentially relies on this one, because we need to blow up a smooth variety, and we have to, I mean, we have to make M to be smooth, so that we can blow up smooth varieties, and we will have good results about the direct push forward. But whether there are other methods to remove this assumption, I don't know currently. This is what I want to remove in the future. And another remark is that, I mean, whether we have to, I mean, for example, if what we can do if we remove the Gisker stable conditions, the answer is yes. We can replace the stability conditions to other ones, like the frame sheaves, like the, I mean, like some relations, like the bridgelet stability conditions. Yes, we can replace this by other conditions. But what we only need is that the existence of the nested modular space, the smoothness of the modular space. This is what we require for our theorem. So that's what I want to share today. Yeah, so that's all. Thank you.
Okay, yeah, thanks for the talk. So any question for the speaker? Yeah, if you have any question, you can directly unmute by yourself or type it in the chatting. Okay, yeah, probably let me answer a question. So actually, okay. I think at the beginning of the talk, you are talking about the quantum toroidal algebra, and it seems that the topological bundle of the nested modular space will play a role as the something like the generator of the quantum toroidal algebra, right?
Yes. Exactly.
Yeah, because I think you defined the something like the nested modular space, and then we should have the tautological line bundle over it. And for that guy, the EI and FI, they are exactly corresponding to the generator. Yeah, to the generator.
Yeah, it's just sorry. Yeah, it's just the generators here, right?
Oh, okay. So how about the HL? HL corresponding to?
I mean, H1 is the universal sheaf. H-1 is the direct due of universal sheaf.
It's a universal sheaf of MK or?
MK times S.
Oh, okay. So EK and FK corresponding to the nested modular space, but HL corresponding to MK.
Yes, because HL, you see that HL is some zeros part, so it should not lift the degree. So it's like the its correspondence is from MK to MK.
Oh, okay.
EK is from MK to MK plus 1, FK is from MK plus 1 to MK. Sorry, MJ plus 1 to MJ. So HL should just be MK to MK.
Okay.
So
yeah,
actually,
thanks. Yeah.
Yes, it is just the derived do. Universal Schiffmann is derived do.
Okay.
Yeah.
Let me see. So, is there any question? Any more question? Okay. So if there is no question, yeah, let's thank the speaker. Yeah. Okay. So.